A huge thanks to Brian for sponsoring this video. Good morning, fellow physicists! Welcome back to another video. Today something really unusual, something that we haven't done often here on this channel. We are going to do mechanics, but not analytical mechanics, just regular mechanics where we do a bunch of forces and stuff on a rotating problem. So, a former student of mine that just started university to become a maths and physics teacher, I wonder why that is. Humble break right here. Showed me one of her problems, exercise problems, that she didn't know how to start off. So I sent her the entire solution because it was quite interesting to me. But she now understood it and I thought it might make for a good video too. So try it out for yourself, and once you're done, keep watching the video for the solution. By the way, this video has been sponsored by the wonderful people on over on Brilliant. More information at the end of the video. And now we are going to dive right in. So the problem is as follows. We have the following constellation. It's just a ball of mass m rotating around a cylinder with a certain radius, small r. The mass in and of itself has a radius, capital R, and overall it's just rotating around it. And what we have to do is we have to calculate the angular velocity for exactly the moment when the mass starts getting away from the cylinder. So it's rotating around and at some point it just starts disconnecting from the cylinder. And we want to find out what the exact angular velocity is for this boundary condition, you could say. And what we are going to do is we are going to sketch everything a tiny little bit more, and we are going to define ourselves a bunch of variables, and then we are going to go ahead and get started. So we have a massless string of length L, we have our mass m, and we also have the cylinder right here, and this mass is supposed to be touching the cylinder. Now this cylinder has a radius of r, so this right here is r, and also our mass has a radius of capital R. So we are going to define ourselves the addition of those two as r hat. This is just what I did to make things a tiny bit easier. And now we need to define ourselves a few conditions here, because we have a string which is rotating. So meaning there are a bunch of forces acting. I am looking for something that I can rotate around. Give me a second. Now rotational problems suck, and I like to solve those using Lagrange formalism. I'm going to make a separate video on that. I already have some ideas using spherical coordinates. It's quite interesting. I got my keys right here. Now, if I spin those keys around, then they start spinning around, obviously. But now, imagine what is going to happen if I were to make it slower. The string is going to basically get from this position right here downwards. Why is that the case? Well, because the gravitational force is acting in the downwards direction. Now, our string is our constraint. It's the reason why our keys don't fly off our mass. Now, there's also another force acting on here. It's a radial force. And this radial force is called the centripetal force. It's the force that is acting inwards. So it's trying to push this key back right to the middle. Those are called components of this force, which is basically holding everything in place. This right here is our constraining force. I'm going to call it Fs for the force of the string, which is keeping our mass in place. I hope this did make a tiny little bit of sense. Now we are going to put this into a little force parallelogram. So let us resketch all of this a tiny little bit more. So what we have right here is our length L, and also we have our mass m down here. Now what we also have is our displacement angle for our rotation. I'm going to call it phi. And also what we got is, on the one hand, our force, which is our constraint by the string. And this force is acting right in the direction of our string up here. So we have this force, F, S, which is acting upwards. It's also a vector in normal case, but I'm going to leave the vector part out. Now, what other stuff do we have? We also have our gravitational force, which is acting downwards, Fg. And we also have our centripetal force, our radial force, pushing the whole mass to the inside once again. Looks like this, Fr. Now what we are going to do is we are going to turn all of this into a little parallelogram. But before we do that, we are going to start off with this connection that we have right here. This right here is a triangle consisting of the forces. Now if you were to take a look at our Fr, for example, we can express our Fr by using the sign of the displacement phi that we have right here. If we were to use the sign of phi, then this results in the opposite divided by the hypotenuse, so Fr divided by Fs. And this does check out just because those are both forces, and if you cancel out the units, it just ends up being a number in and of itself. Now we can solve for Fr to get ourselves a better expression for that, and Fr is hence Fs times the sine of phi. Okay, what that just means is that Fr is just a component of our constraining force Fs. Since the sign is between 0 and 1 or -1 and 1, depending on your coordinate system, this just means that Fr is always just a small part of our total force Fs, which is keeping our mass in place. Now we are going to do the same thing here. If we were to make this a tiny little bit longer, just for clarification purposes, we can project our triangle once again into here. Now what you're going to notice is that this right here is a 90-degree angle. So if this right here is phi, then this right here is, for example, alpha. Now what we also know is, since this right here is a right angle once again, we have our opposite angle right here, which is alpha once again, and this resulting in this down here being 180 degrees minus 90 minus alpha is just phi once again. Now we have our next connection, namely we can express ourselves Fg by using once again our constraining force Fs. This right here is the projection of our force that we have up here, and the cosine overall. So we are going to get the cosine of phi is equal to Fg divided by Fs, adjacent divided by our hypotenuse. And once again we can solve for the component of the string force. This time our vertical component is Fg, the gravitational force, Fs times the cosine of phi. And this right here is basically the key to the entire problem, and we are almost done. Because what you're going to notice now is that we don't even need to know the constraining force Fs. It really doesn't matter, because if we were to divide both of those equations by one another, we are going to just cancel out Fs to being 1. So if we were to divide those equations, then we are going to get Fr divided by Fg is hence equal to the sine of phi divided by the cosine of phi, which is the same as the tangent of phi. You can express it like this, but we are not going to do so because we want to get ourselves the angular velocity, and we can actually cancel a bunch of things out and substitute a bunch of things to get ourselves a very, very nice expression for z speed. Now, at first, what we are going to do is we are going to substitute our radial force in and our gravitational force in. Now, Fg, we all know that this is just m times g. But what about the radial force? The radial force is, by its formula, m times v squared divided by r, where v is the same as our angular velocity. No, it's just the radial velocity. I'm terribly sorry. This is the radial velocity. Now, just think about the velocity in general. It's the same as s divided by t. We have our distance divided by the time. It's the change of distance over time. Now, if we were to go in an entire circle, what is the distance that our movement is going to make? So in this problem, an entire circle, well, it's going to be the circumference of the circle. So 2 times pi times r divided by, and how long does it take to get around 1? It's just the period time, capital T. Now, 1 divided by t by definition is the frequency, so we can substitute this for 2 times pi times the frequency times r. Now, 2 times pi times the frequency by definition is the angular frequency, or otherwise known as the angular velocity. So this right here is the same as omega times, and our radius r that we are having in our problem for our mass is exactly r hat. So this was just a very quick derivation. You are probably familiar with all of those things already if you are into physics a tiny little bit. Now we can substitute everything in, and we're going to get for the radial force that this is m times omega squared times r hat squared, and also divided by our radius r hat, where r hat is going to cancel out, leaving us with m times omega squared times r hat. And this right here is a well-known formula for the radial force. Now we can plug everything in, m times omega squared times r hat, where the mass is going to cancel out as usual in those problems involving some kind of forces on a string. And this right here is what we want to solve for omega, because this is what we are looking for, the angular velocity. Now this is easy to do. Multiplying both sides by g and dividing both sides by r hat is going to result in omega squared being equal to the sine of phi divided by the cosine phi, or otherwise known as the tangent of phi, times g divided by r hat. Now by taking the square root of all of that, we are going to get ourselves the angular velocity. But this is not a very good expression, because finding out the angle phi is kind of annoying. Try it in an experiment, it's not going to be a pleasure when it's rotating. So we need to find a different way. There's got to be a better way. And there is, because our angle phi is actually part of this right triangle that we have up here. And we know a bunch of things about this exact right triangle. Namely, the hypotenuse is L, we have our angle phi here, and the radius of our movement is just r hat. Meaning we are going to end up with the sine of phi being equal to r hat divided by L. And this is very good, because in our formula for the tangent, we already have a sine of phi, but the cosine of phi is the problem. But it's actually not, because we have the fundamental theorem of trigonometry, which says that the sine squared plus the cosine squared is nothing other than 1. And we can actually solve this for the cosine by subtracting sine squared and taking the square root, giving us that the cosine is equal to the square root of 1 minus sine squared. All of this with respect to phi, obviously. And now we can plug everything in. We know what the sine of phi is. This is nothing other than r hat divided by L, so giving us the square root of 1 minus r hat squared divided by L squared. And now we can plug this in and simplify it a little bit, and then we are done. Giving us overall that the angular velocity is hence the square root of g divided by r hat. Then we have the sine of phi, which is r hat divided by L, and then we have this expression right here. Square root of 1 minus r hat squared divided by L squared. Now r hat and r hat is going to cancel out. We're going to drag the L down into the denominator, giving us overall that omega is equal to the square root of g divided by L times the square root of 1 minus r hat squared divided by L squared. And what we can do is a bit of black math magic. L is a positive side length, so that's the same thing as the absolute value of L. And the absolute value by definition is the square root of the quantity squared. And the square root is multiplicative, so we can drag it to the inside, leaving us overall down here with this expression as being the square root of, and then we have L squared minus L squared times r hat squared divided by L squared, where L squared is going to cancel out, giving us a beautiful final expression for omega, being the square root of g divided by the square root of L squared minus r hat squared, where r hat, by our definition, is small r, so the radius of the cylinder, plus capital R, which is the radius of our mass. So by substituting this in, we are going to get r plus r squared down here, and this concludes the problem. And maybe this is also what you have found out and what you have posted down there in the comments below. I thought that this is a very fun problem, and as mentioned before, I'm gonna do another video continuing this using Lagrangian mechanics, using a spherical coordinate system, which is kind of rare to find because most professors at university just put one of those exercises in, just for fun and then never touch it again because it's kind of annoying with spherical coordinates. But it's a good example. I'm going to post it here and I hope you are interested. And if you want to see more physics, mathematics, whatever it is in the STEM field, then the contents of today's sponsor Brilliant might be the perfect fit for you. In order for us to deal with physics problems like those, it's very advantageous to draw out all of the forces and to use visualizations to our advantage. And this is where Brilliant comes really in if you are a visual type of learner. Brilliant is your source for some of the best online learning content that you can find out there on the internet. Doesn't matter if it's the mathematics and physics that we did today, computer science, chemistry. No matter what it is you are looking for in the STEM field, Brilliant got you covered with their over 70 interactive courses. The course concept is simple but extremely effective. Take visualizations and use them to your advantage, such that you can get a better grasp of the problems at hand. And Brilliant is very good at identifying how far you have come in your studies. Create an account, tell them how far you are in your university studies, and they are going to set a starting point for you. Are you a new learner? Doesn't matter. They are going to make it easy for you to learn something new on a daily basis. Are you an advanced learner? They are going to figure that out and going to give you the appropriate topics and also exercises to get you further in your studies in no time at all. Their visualizations are amazing. They are an absolute game changer in the online learning content world, and you should try it out and see for yourself if it's something for you by using my link here at the top of the description, brilliant.org/flammymath. Try it out, the whole landscape of Brilliant, for entirely free. And if you feel like this could turn into a long-term relationship between you and their services, then definitely make sure to use my link in its entirety and get 20% of an annual premium subscription. They're very good at what they do, and I highly recommend it to everyone who wants to learn something new on a daily basis, on the go, in a mobile app, or at home on your computer. Check it out, support the channel this way, and I would like to thank Brilliant once again for sponsoring my video. Other than that, I thank you guys for watching. Have a flammable day and please stay safe during the Xmas season. See ya.